Figure 1.14 Fracture toughness of steel under impact testing. From ductile to brittle behavior greatly reduce the toughness of the materials. While this could be determined by evaluating the stress strain diagram at different temperatures, it is more common to evaluate the toughness of a material with an impact test that measures the energy required to fracture a specimen. Figure 1.40 shows how the energy required to fracture a mid-steel changes with temperature. Flynn and 2019 and 95. The test results seen in Figure 1.14 were achieved by applying impact force on bar specimens with a detect a simple V-knot machine into the specimen's ASTM E23. During World War II, many Liberty ships shrank because the steel used in the ships met the specifications at ambient temperature, but became brittle in the cold waters of the North Atlantic. In addition to temperature, some materials, such as viscoelastic materials, are affected by the load duration. The longer the load is applied, the larger is the amount of deformation or creep. In fact, increasing the load duration and increasing the temperature cause similar material response. Therefore, temperature and time can be interchanged. This concept is very useful in running some tests. For example, a creep test on an asphalt concrete specimen can be performed with short load durations by increasing the temperature of the material. The time temperature shift factor is then used to adjust the results for lower temperatures. Viscoelastic materials are affected not only by the duration of the load, but also by the rate of load application. If the load is applied at a fast rate, the material is stiffer than if the load is applied at a slow rate. For example, if a heavy truck moves at a high speed on an asphalt pavement, no permanent deformation may be observed. However, if the same truck is parked on an asphalt pavement on a hot day, some permanent deformations on the pavement surface may be observed. Work and energy. When a material is tested, the testing machine is actually generating a force in order to move or deform the specimen. Since work is force times distance, the area under a force displacement curve is the work done on the specimen, where the force is divided by the cross-sectional area of the specimen to compute the stress, and the deformation is divided by the length of the specimen to compute the strain. The force displacement diagram becomes a stress strain diagram. However, the area under the stress strain diagram no longer has the units of work. By manipulating the units of the stress strain diagram, we can see that the area under the stress strain diagram equals the work per unit volume of material required to perform or fracture the material. This is a useful concept, for it tells us the energy that is required to deform or fracture the material. Such information is used for selecting materials to use where energy must be absorbed by the member. The area under the elastic portion of the curve is modulus of resonance is the amount of energy required to fracture a specimen is a measure of the toughness of the material, as in Figure 1.15. As shown in Figure 1.15, a high strength material is not necessarily a tough material. For instance, as discussed in Chapter 3, Increasing the carbon content of steel increases the general strength but reduces ductility. Therefore, the strength is increased, but the toughness may be reduced. Failure and safety. Failure occurs when a member or structure ceases to perform the function for which it was designed. Failure of a structure can take several modes, including fracture, fatigue, general yielding, bucking, and excessive deformation. Fracture is a common failure mode. A brittle material typically fractures suddenly when the static stress reaches the strength of the material. When the strength is defined as the maximum stress the material can carry. On the other hand, a ductile material may fracture due to excessive plastic deformation. Many structures, such as bridges, are subjected to repeated loadings, creating stresses and that are less than the strength of the material. Repeated stresses can cause a material to fail or fatigue. Other stresses were below the strength of the material. The number of applications as material can withstand depends on the stress level relative to the strength of the material. As shown in Figure 1.16, as the stress level decreases, the number of applications before failure increases. Ferrous materials have an apartment endurance limit or stress level, below which fatigue does not occur. The endurance limit for steels is generally in the range of 1/4 to 1/2 the ultimate strength. Another example of a structure that may fail due to fatigue is pavement. Although the stresses applied by traffic and are typically much less than the strength of the material, repeated loadings may eventually lead to the loss of a structural integrity of the pavement surface layer, causing fatigue cracks as shown in Figure 1.17.